This poster presents an aluminum-assisted magnesiothermic route that forms Ti3SiC bows with higher phase purity in minutes and explains why it works. Max phases are attractive because they merge metallic and ceramic traits, yet conventional syntheses often demand long furnace schedules or hot pressing. Our goal was to keep the infrastructure simple, tighten the reaction window to about 5 minutes, and use a small AL addition to steer the path toward Ti3SiC2 rather than competing carbides and silicides. The processing concept is a wafer-pellet-wafer sandwich that couples intimate contact with a controlled exotherm. Powders of Ti, Si, and exfoliated graphite were mixed at a 3:1.752 molar ratio with 10 W% Al, pressed into 12 millimeters pellets, and clamped between two magnesium wafers of 2.5 centimeters diameter and 1 centimeters thickness. The assembly sat in flowing CO2 at 500 centimeters breakers per minute. Ignition used a graphite electrode with an AC arc welder, and the reaction was allowed to run to full mg consumption before cooling. The post-treatment is intentionally minimal to keep barriers low. The reacted pellet was cleaned in 20% HCl to dissolve MgO and other soluble products, then ground for characterization. This workflow favors reproducibility, short cycle time, and compatibility with common lab hardware rather than specialized atmospheres or pressure vessels. The phase analysis shows Ti3SiC2 as the major phase with a controlled TIC fraction. XRD index by standard databases confirms hexagonal Ti3SiC2, space group P63mm, coexisting with cubic TIC FM3M. Quantitatively, we obtain about 75% Ti3SiC2 and 20% TIC. The Scherer analysis after instrumental correction gives an average crystallite size of 34.74 nanometers for Ti3SiC2, which is consistent with fast nucleation and limited growth under short thermal spikes. The microstructure supports the coexistence of nanocrystalline max with micron-scale carbide. SEM reveals agglomerated, roughly spheroidal particles, with TIC centered near 1.4 micrometers in size. HRTM shows fine agglomerates, and FFT indexing matches the assigned phases. EDS mapping indicates homogeneous distributions of Ti, Si, C, and detectable Al within the aggregates, in line with the intended stoichiometry. The mechanistic interpretation is that Al acts as both flux and deoxidizer, while Mg supplies the exotherm and reduction potential. Aluminum lowers local melting and promotes interdiffusion that favors max nucleation, while it also scavenges oxygen that would otherwise stabilize parasitic phases. The magnesium wafers ensure intimate reactive contact and high activity, and the CO2 sweep manages gas evolution without acting as an oxidant under these conditions. The residual TIC is attributed to carbon activity and brief overtemperature excursions during ignition. The advantages over conventional routes are speed, simplicity, and improved selectivity at low cost. There is no hot pressing, no high-purity inert glove box routine, and no long furnace holds. The 5-minute cycle and commodity inputs make this attractive for iterative screening of compositions and for scale-out in modest facilities. The limitations are clear and define the next optimization loop. To further depress TIC, we will tune Al content, wafer thickness, pellet green density, and ignition energy, and we will add simple hold time control. We also plan Rietveld refinement with an internal standard for formal phase quantification, and we will explore pre-alloyed TiSi powders to bias the path toward Ti3SiC2. The broader impact is a transferable protocol for rapid max phase synthesis that can feed directly into property testing. With purity improved, we will move to oxidation kinetics, thermal shock, and device-relevant evaluations to benchmark performance against furnace-based materials. In closing, an Al-assisted magnesiothermic sandwich delivers nanocrystalline Ti3SiC2 at about 75% purity in a 5-minute cycle, with a clear lever set for further improvements. We view this as a practical bridge between exploratory max chemistry and scalable processing suitable for aerospace, automotive, and energy components.